Cool, thanks Helen. Yeah, I'm going to talk about digestions and different types of digestion and where they fit into the analytical process. Right, quick overview of the generalized process flow of a minerals laboratory and where sample digestion actually fits into that. First of all, as Helen, just to reiterate what Helen said, sample receipt and registrations first. Then we have sample preparation. And the product of sample preparation is a dry, fine, homogeneous pulp. Then we have sample digestion. Feed it into an instrument and do your QC. Why do we do sample digestion? Simply because the instruments we use commonly in a laboratory, you cannot feed them dry, fine, homogeneous pulps. And we have to generally get it into a solution, or in the case of XRF, we make what we call fusion discs or glass beads. Okay, what are the implications of using total and incomplete methods or partial methods? Well, total digestions are what are known as rational methods, and essentially the results are independent of the digestion method used. Whereas the incomplete or partial digests are empirical methods. And this is very important that we remember this. The results are dependent on the conditions of the digest. If you hit it harder, you're going to get more out. If you get all of it out, okay, you've got all of it out, you can't get any more. But there are a lot of elements that you can hit hard and you can hit not so hard, and you can get different amounts out. And there are many variations on the same digestion. Take, for example, aquaregia. There are a lot of labs out there, a lot of companies doing aquaregia digestions, and they all have different recipes. They've got different recipes. They're going to get different numbers for a lot of the elements. And if you want to compare two sets of data, bear this in mind. Just some quick safety considerations. If you might be involved in mine site design, for example. Acids are particularly dangerous. They can burn you. There are risks of fire or explosion with perchloric acids. You've got fumes that you have to deal with. You need special extraction systems with perchloric acid. Fusions obviously have the flux hazards and the heat hazards, but generally on mine sites people prefer fusions because they are less hazardous and safety is of paramount concern. Right, let's launch into the 4-acid digestion. What are the 4 acids? We've listed them there: perchloric, nitric, HF, and HCl. It's a staged digestion. We don't all throw it into a beaker or a test tube and stand back. First of all, we add things like nitric acid to oxidize the sulfides to sulfates and retain the sulfur. It's applicable to low-level geochemistry and many ores. Minimum contaminants. You're doing the digestion in Teflon. It's a low dilution. You can get your low detection limits. HF dissolves most silicates, in fact, almost all of them. And what you're doing is essentially converting your sample to a soluble perchlorate form of your sample. And you leach that up in hydrochloric acid, and you take it across to your instruments. There are some limitations with 4-acid digest. What are these principally? First of all, some minerals do resist 4-acid digests. I'm not saying they will not dissolve, but you cannot guarantee they've all dissolved in your 4-acid digest. I've listed some of them there. There are not too many of them. Those are the main ones. Secondly, some elements precipitate at low dilutions, and particularly lead, silver sulfates, lead silver chlorides, barium sulfate, potassium rubidium as perchlorates. They're kind of one of the exceptions that perchlorates are generally very soluble, but potassium rubidium, not so much. And some volatile elements are lost. Silicon and boron are lost as volatile fluorides, and there's some other elements that are lost, partially lost, not all lost. Moving on to 3-acid digests. Those are the 3 acids. You'll note the emission of HF, and that's why they prefer that on many mine sites, because they don't like working with HF. Because you don't have HF, a lot of silicates will be partially dissolved. It is generally more aggressive than acarejia, and it's effective against many sulfides, oxides, carbonates, and particularly a lot of sulfide ores, and that's why it's very popular on mine sites. Let's move along to acarejia. As Helen mentioned, a 3 to 1 or 1 to 3 molar mix of nitric and hydrochloric, and it forms nitrosyl chloride and chlorine in the solution, which is a powerful oxidizing and complexing reagent, and it dissolves a lot of mineral species. It dissolves precious metals, and nice thing about acarejia, it's amenable to upscaling. You can do big samples like 25 grams or 10 grams, and you get your gold, platinum, palladium coming out in the wash, and most of the gold is dissolved. Roughly about 95% of what you get out in fire assay is dissolved in acarejia. But remember, it is not very effective against many silicates, and is not very effective against refractory oxides, things like rutile or ilmenite. And it's not selective. That's a mistake people make. I often get a lot of people sending in, for example, nickel, copper nickel, magmatic sulfide ores, and they want us to do it by something like acarejia, and they believe that we'll get the sulfide component of the nickel out, but not the silicate. Yeah, not really. It's not selective. It will leach something out of the silicates and most of the sulfides. There are better ways of doing that if you wanted to do that. And there's a very wide range of recovery for different elements. For example, copper, generally mostly recovered, whereas something like zirconium, very poorly recovered. We've got some examples just now. Moving on to something like a cyanide leach. Two types. We deal with a bleg, and that's a very low-level analysis, great for soil, stream sediments. I've seen some marvelous calcrete examples with blegs, and has very, very low detection limits, 10 parts per trillion. That's good. And there's a big, a lot of people are looking for mini blegs. They screen out the very fine fractions, and they send it in for a bleg. You don't need a kilo like a normal bleg would take. You can do it on 50 grams, no problem, and very good numbers coming out of that as well. Now moving on to the leach well. It's an accelerated cyanide leach for gold ores, and what it does is determine the cyanidable gold in a sample. And we can take the tails from the leach well process, and we can dry them, rehomogenize them, wash them, dry them, rehomogenize them, and put them through fire assay, and you can get a very good idea of what's refractory and what's amenable to a cyanide process in your ores. Things like acid-soluble copper and cyanide-soluble copper, these are classic partial empirical techniques. The acid-soluble copper uses a sulfuric acid leach, and again, remember, there are no standard procedures or additives. A lot of them have things like ferrous sulfate added in it, and they all have different times, temperatures, and they all get different amounts of copper out. And we have, I think, about 20 of these different recipes on file at the moment, and you can pick and choose or give us your own. We can do it. But most copper oxides or carbonates are soluble, and sulfides are poorly soluble. Something like a cyanide-soluble copper, which has very important metallurgical implications for the fact that it does use up your cyanide. Again, no standard procedure. Most copper minerals are soluble with the exception of chalcopyrite and chrysocolla. And then you can hook them up together as a sequential digest. First of all, get your acid-soluble copper, and the tails of that process goes into your cyanide-soluble copper, and then they do a 4-acid on the residue. And partial selective digest, I'm going to go over this very quickly. Normally you target the A horizon in soils. What are we doing with them? We are looking for buried mineralization. Ions move through the substrate. The substrate can be something that's moved in, for example, laterite might have moved in from somewhere else, till, or for example, Aeolian sand, and the ions make their way through the substrate and they coat the grains, so goes the theory. And what we do is we're not interested in the chemistry of the substrate, we're just interested in the chemistry of what's actually on the surface, the exogenous labile ions. Fine fractions. That's a common theme that we seem to be hearing an awful lot of late. They work best, lots of reaction sites, big surface area, devoid of barren phases like quartz and feldspar, and different digests work in different settings. Some of them are listed over there. Moving on to fusion digests. Well, fusion digests guarantee total dissolution. Okay, so they're great for refractory elements, for refractory minerals, should I say. What happens is you mix the sample with a flux, and the sample dissolves in the flux when you put it in the muffle, just like sugar dissolves in water. And then you dissolve the product or the fusion process in an acid. The disadvantage of the flux is now you've got all that, the disadvantage of the fusion is now you've got all that flux in the solution, and you also have, the crucibles give off a lot of metals. So they will compromise, well, they will preclude analysis of those particular elements. They come in a number of flavors, principally the lithium borate fusions. We analyze them in platinumware, and they're ideal for whole rock analysis. Sulfides are not particularly kind to platinumware, although there are tricks of the trade to limit the damage. And then we get the sodium peroxide fusions, which you do either nickel or zirconium, highly oxidizing and suitable for almost all samples, including sulfide ores. Just remember, if you're doing something like sodium peroxide, you now have sodium in the solution. If you do it in zirconium, you'll have like zirconium and hafnium in solution. So there's a lot of elements that are excluded by the process. XRF fusions. What are we doing in XRF? We're dissolving the sample in a piece of glass. Now, why would you want to do such a thing? Simply because, just before I get onto that, XRF is a total analysis. The XRF part, not the fusion, makes it a total analysis. And we get rid of what we call physical effects, particle size and mineralogical effects. Severely compromise XRF accuracy. So if you get rid of the interactions that X-rays have with crystals or minerals, you get a far better analysis, and the corrections you need to make are relatively simple and can be done by the computer. Whereas if you try and correct for powder analyses, it gets very messy and they're very difficult and the data are not particularly good. Just an example what fusion discs look like, typical silicate, 40 millimeter diameter piece of glass, and there's an iron-rich sample. Alrighty. Fire assay, it's a very robust process which concentrates precious metals, basically gets rid of everything in your sample that's not precious metals. And you get very close to quantitative recovery for gold, platinum, palladium in the traditional lead collection fire assay. Typically use a big sample, which if you want to lower your variance on your sampling error, that is a good thing. Materials like chromatites and copper concentrates, for example, we're going to use a smaller sample, so you're not going to do a 50-gram fire assay on a copper concentrate unless you do it 5 times and put all the buttons together. The 2 stages to fire assay. Firstly, you collect the precious metals in a piece of lead, and that's called your button. And secondly, you get rid of the lead by a process called cupellation, and you put it in a magnesia cupel, and you're left behind with the precious metals. What happens is the lead oxidizes, the magnesia cupel absorbs the lead oxide and leaves behind the precious metals a little bead called a prill. And you can see that one didn't work very well because it had tellurium in it. But yeah, fire assays are trained to look for these kind of things. It's not an infinitely robust process, but it is very robust. And typically when things do go wrong, we can pick it up. The alternative is the nickel sulfide collection fire assay, where you can do gold, platinum, palladium, osmium, iridium, rhodium, and ruthenium. Just some quick graphs on, before we wind up, on different digests and recovery. These are Aurea's reference materials. And looking at your chalcophile elements, remember Goldschmidt's classification from earlier, and there's some cobalt and nickel, which aren't strictly chalcophiles, but basically with a 4-acid digest and acarige, you get reasonably good recovery on chalcophile elements. Not always. For example, the lead there might be in the silicate, for example, and you would not recover it very well with acarige. Majors and lithophile elements, this is where acarige starts to... Oh, I'm running out of time. 1 minute. Oh, can I have a minute? Okay. Acarige struggles, and high field strength elements, you can see acarige is really struggling. And rare earth elements, what we take away from that is heavy rare earths are more difficult to extract than light rare earths with acid digests, and your rare earth patterns might look different. And just to wind up, if you're doing your QC like one should, and you can try it in an acarige process, it might look very good. But if you control it on what the process doesn't do, for example, what you got off the certificate, but if your empirical method doesn't do what's on the certificate, you might get a whole host of failures that are not particularly useful. But yeah, that's only because you're controlling it on the wrong parameters.
Thank you, Richard.